soon. All right, we're on the air. This afternoon I want to discuss a little bit about the HAL assembly language, which stands for Human Assembly Language. And this is my result of doing assembly language on Linux and OS X and then with Windows. They're different, but it goes beyond the differences. I found it frustrating in many ways keeping track of the registers, even when you're dealing with one system. Which register is the third parameter for a function call? Which is the fourth? Which registers must you save if you want to use them in your function so that the calling function can depend on it? Those things are kind of frustrating. Which ones are available that you don't have to save? Well, I've got my plan. And let me start with the Hello World program. And I need to get screen sharing to work. All right. What I've done is I've got an include file that I'm calling how.inc, and it provides macros that take care of a few things. One thing is I decided I would rename RBP to RFP for frame pointer because it just makes more sense to me. That one's kind of crazy, not too important. But here's another one. I got tired of trying to remember which one of these registers was the one for the first parameter. So PAR1 means the first parameter, and adding a D to it, it's a double word equivalent of that register. So here I'm moving a 1 into parameter 1D. That's the same whether it's Linux or Windows. It gives you a different result. For Linux, you'll get EDI. For Windows, you'll get ECX. So this works either place. For parameter 2, PAR2. So I can do load effective address PAR2, and I can get it to be RSI for Linux and RDX for Windows. Parameter 3 is PAR3. The way these things are done internally is using %define, but it's a little more complicated than that. You can give it a name here like stuff and make that be equivalent to RAX. But the way I've defined it, I have the register like PAR1, and I also define PAR1Q for the 8-byte quantity along with PAR1 because I don't like typing NQ. And I've got PAR1D, W, and B, and for the ones that have a high byte thing, I also have an H suffix added to the registers. So this code, as far as I can tell, looks like it would work fine with Linux or Windows. Let's put a breakpoint on here. Oh, I've got one. All right. Hard to keep track. All right. And I've updated EB to include the HAL registers, which are the same registers, just having different names. And you can see they're organized in groups. If I want to know which registers are for parameters, with Linux there are 6, PAR1 through PAR6. The return register, I started calling it RETQ, but I gave up on it, and I finally thought of ACC for accumulator. So ACC is the address for return values and whatever you might use RAX for. SCR stands for scratch registers. Turns out there are 2 of them. And the registers which must be saved for Linux, there are 5 of them. Do I really care what their names are? If you flip back over here, you can see the original names for these registers. And if we step forward one, then we see that looking at it this way, just one? That doesn't sound right. Oh, parameter 3. Parameter 3 is RDX 13. All right. Parameter 3 here is a 13. I like it better, PAR3. Now, if you were doing this for class, I would recommend you prove using the new names with the teacher before you did it, but if you're just kind of curious about doing it this way, then it seems perfectly fine to me. Now we've got parameter 2 and parameter 1, if it'll click, a 1, and parameter 1 for write means write to standard out, then call the write call, and on the terminal we see it says hello world. All right, so we've got a different way of writing functions. Now this macro is a little bit unusual. What it does is subtract the appropriate amount from RSP. And for Windows, there are 4 locations that must be maintained above the stack pointer for the possibility of you having to copy the 4 register parameters into memory for Windows. So for functions that use the var args or standard args macros, it's easier to write those macros if all of the parameters are in an array in memory. So if you provide 4 quad words, these 4 registers, PAR1 through PAR4 for Windows, can be copied into that space. So, going back to the reserve statement, the first value here is the number of local variables that you want to use in the function. And I've got local variables with equates that give us local 1, local 2, local 3, local 4, etc. that work. For Windows, there are 4 locations above the stack pointer that can use positive offsets. That would be starting with plus 16, plus 24, plus 32, and plus 40. I guess it gives us 4 of them. And for Linux, they're not. So it would be inconvenient keeping track of how to use those 4 quad words for Windows. But the reserve stuff and my equates for local 1, local 2, etc. work fine for it. Now for the local variables that are, if you had for Linux, if you were to, let's change this and say we wanted 4 local variables. Now when we run this, the first instruction is this reserve instruction. And if you'll notice, RSP ends in 40, and now it ends in 20. So it subtracted 32 bytes, or 32 from RSP. So it made room on the stack for 4 values. And for locals, my intent is that these would be named and used with plus local 1, plus local 2, plus local 3, plus local 4. And in fact, local 1 would be negative on Linux and positive on Windows. So it works fine. The second parameter, which is optional, is for the number of parameters, maximum number for functions that get called in your code. So here I'm saying I'm using 3 of them, so there's no need with 3 to have any additional space on here. But if I were to change it to say that I wanted 10 parameters, that would mean that I would have 4 more. And if I run it now, let's see if the arithmetic's right. Yes, it subtracted 64. I have 4 locals and then I've got 4 parameters. Now, if you've got more than 6 parameters, you have a little challenge in naming these other things. There are parameters that would be past the 6 for the current function, and parameters possibly past the 6 that are register parameters for the function you might call. So I can't call parameter 7, 8, 9, and 10 in a simple way. I've got to distinguish whether it's the current function or called function. So I named these CURR-PAR1, and I used a capital P for the, CURR-PAR7 for the first one of the stack-based parameters for the current function. And I've got new capital PAR7 for if I'm going to call a function. So I've got those things available. And the biggest thing here is we don't have to remember hardly anything about registers. We've got scratch registers. We need to know there are only 2 of them, but I guess you won't succeed in using SCR3. And you probably need to know that there are 6 register parameters for Linux and 5 of the save registers. I found it difficult keeping track of which ones are the ones you have to save. I could remember these 6 because I've done so many functions and I've got that memorized. No big deal. Which ones are the scratch ones, I don't remember. If you're curious, the view menu has another little table called HAL names, which can be brought up, and we can see the corresponding names. Register 10 is scratch 1, register 11 is scratch 2. I think those are the same with Linux and Windows. And in fact, the save parameters 1 through 5 are the same, but Windows only uses 4 register parameters. 4 parameters per register, 4 registers per parameters, that's the right order. So the other 2, RSI and RDI, those become save 6 and save 7 under Windows. I can't make them have the same use for functions, or how they call functions, but I can do something about it. All right. Let's close this file. And let's tell it to save this thing with a name, and I want to do something with arrays. So how about arrays.how? All right. There are 3 different varieties of arrays that you can use. Arrays that are in the data segment. And to have an array in the data segment, you have to define data. So you could have the array X, which you can do data quads just to keep it simple. 1, 2, 3, 4. Oh, I left out 3. How about 3, 4? And you can also, if you wanted a more exotic array, you can do, what is the word? Not repeat. Shoot, my brain is forgetting. Does anyone remember the thing you have to do to repeat a declaration some number of times? I think it's times. That may be it. Let's see if it's right. Times 5 DQ7. Okay, none of the source files defined main means that it assembled the file fine, but this file, I guess I should make these be the same size. 6 times 7, so I got 6 7s in the array Y. And the other type of array that you can do that's static is in the BSS segment. So let's put the sum of these two arrays here. And here you get reserve and Q for quads. And you tell it how many you want to reserve. Looks like 6. I can't type. 6 would be the right size. Now, when the BSS segment is created, all it does is allocate memory in the program when the program starts, and I believe those are all zeros, which has a lot to do with the fact that static variables in C or C++ have 0 for their initial value. All right, so we'll do segment dot text and global main and now we've got a main, so let's do the standard thing, except I'm going to do push RBP instead of RFP, and then move RFP, excuse me, I'm reverting to my old habits. Move that in there and reserve so that I can write portable code. I don't have any use for local variables at the moment, so I'll just do reserve 0. I'm not going to call any functions immediately, so there we are. And leave ret is a valid function, so let's see what happens if we execute a simple program before we do anything with arrays. Instruction expected after label on line 5. What have I done wrong? Is that a Q? I believe it is. Yep. All right. So now it assembles and the program runs, and we have, well, that's interesting. I've got RFP instead of RBP. Well, I'll leave that for now. It doesn't really matter what the value is, but it's easy to change. I've been juggling these things, and I just screwed up the naming, I guess, the last time I built or changed the way this stuff is laid out. My original set of registers was a 4x4 table, and then 2 more down below. Now it's a, well, this made it also in 5, I guess. That one's pretty handy. All right, so let's do something. If we want to do a loop, for I equals 0, I less than 6, sum bracket I equals x bracket I plus y bracket I. My strategy for writing assembly code is generally, though I may not do it every time, it's generally, at least in my mind, that the idea is to write C code and then translate it. So if I'm going to do a for loop, I need to have some register that is going to be for I. That sounds like a scratch register. So I'll XOR or exclusive OR that thing with itself to make it equal 0. And then I need a test. If I'm going to do it exactly like it says, I need the top of the loop to be, whoops, Control Z. I'm going to go back to the top of the loop, and I want to compare scratch 1 versus 6. And if it happens to be greater than or equal, I want to jump past the loop. So another way of saying it, jump not less than to the end of the for loop. All right, does that look pretty good? By using a not with the less than, I get the same word, less than, not less than. Sometimes my brain will be less confused by that. Now, if I'm going to add two values together, how about I use the accumulator? Move the value from x. Oops, I don't want to use x. Yeah, I do. X plus 8 times, it was SCR1, right? And then add to the accumulator y plus 8 times SCR1. Now, the 8 that is here, the value that you could use has to be either 1, 2, 4, 8. And those are powers of 2. So the value that is used internally in the CPU is shifted by 1, 2, or 3 positions on the way to being used to form an address. So there's no real loss to that. And then we've got the sum. We want to move the sum to the sum array plus 8 times SCR1. And before we do the leave, we might as well tell it to zero out the register that's going to be used as the return value. This code will work fine with Linux or Windows. Now, well, it won't work too well unless I get for end into the program. Left that out. Define a variable for sum so we can see the values change, and this needs to be a long, which is an 8-byte thing. Tell it that is an array variable and that the indexes should be 0 through 6. Through 5. 6 would work, but it's kind of cheating. View data. Oh, data's already here. All right. So we can see we now have the sum array visible here, and it's zeros at the start. So we were somewhere in this program. All right. So now we have zeroed out scratch register 1. And I don't know which one scratch is, but I can see we've got a successful value of 0 there. Compare it against 6, and we get sign bit set, or the sign flag is set, so it means it's a negative. All right, then we move SCR1 is a 0, so the address that is in brackets here is the address of X. I don't really care what the address is, but that works. And we've got 1 in the accumulator, And then if we add to that the value that's in the address y, that y has 7s everywhere. Then we can move that to the sum array. And we should see an 8 there. Ooh. Oh, we're looking at the wrong piece. All right. Scroll down. Well, it's not showing my sum array. I don't know what happened to it, but I would call this a bug. It should be under user defined. I will do it one more time, then I'm going to quit worrying about that and move on, because I know it worked properly. It's just I've screwed up somewhere in defining this thing. Well, maybe I've got to tell it to expand the user. Oops. All right, I'm going to give up on figuring this out immediately and solve this later today, probably. I don't know where it went, but it doesn't have a scroll value, and it probably isn't going to be visible no matter what I do. These little greater than symbols usually allow you to expand things, and sum is not there, though it says array variable. This doesn't make a lot of sense. I don't think this is the sum array. No, this is ignorance. All right. So I'm going to ignore that for the moment. All right. So we can continue to do things. Did it do that one time? Oh yeah, it did do it one time. To have a successful for loop, I've got to go back to the top of the loop. Now I'll follow it through and observe it working correctly, I think. I find it a little less reliable to write assembly code than C or C++ code. I tend to get those right, but assembly I screw up too many times. There's just too many ways to do it. Jump back to the top of the loop. Guess what else? I forgot to increment the scratch register. Scratch register still 0, so I've got an infinite loop. Unbelievable. Increment. I think it's INC and SCR1. Now scratch register has a 1 in it, and we'll go back in, and when we move the next value into the array, we had a 2, and remember we have 1, 2, 3, 4, 5, 6 in the X array, and we add 7 to it, and I will click enough times, I think, to finish this. I don't know. It makes you happy when you actually quit on the correct iteration of the loop. I got a 4 in there for scratch 1 right now. 6. Compare, and at this point we got ZF or 0, jump not less than 4n. A, we go to the 4n. So it did the correct number of iterations. All right. What does this feel like compared to using the original names? What do you think, Paul? Well, it doesn't matter. All right. there's one other type of array that you could use, and that would be for an allocated array. So let's get rid of this stuff. And I've got some stuff in here that doesn't need to be here. All right. So to allocate an array, you can have more data. So I've got arrays X and Y, and I may as well have a sum array, and I will make the sum array be stored as just a pointer in the data segment. All right. So if we're going to use a function to allocate some memory, my choice would be malloc. And we need to call malloc with the number of values that we want to work with. Let's set that number. Let's call it n. That seems sufficient. So we want to allocate PAR1. We want to move that from a memory location in. Is that what we want? In the memory location, you need to use it directly. All right, so there we are. We move it into there, and then we need to multiply it times 8. And the easy choice is to shift it left. Shift left, PAR1, move it, shift it 3 bits left, and then call malloc. And let's see this behave. Ooh, undefined symbol malloc. That's a little different. I've typed it in with global up here with main. I'm not defining malloc. I made another little glitch. I need to tell the assembler and linker that malloc is something that should be resolved externally. So I need it extern instead of global. All right, now, ooh, what's wrong there? Assume it's going to be the same thing. If we try it without the brackets, what do you get? 0. Is n something special? Perhaps it's not the n that I have declared. I've run into a few little glitches. Oh, that's n. Yeah, now I haven't defined an n, so n looks like it's a forbidden name for me today. Num. Okay, so if I just do move with num, I get the address of num. And if I do the move with the brackets, I get the value that is at that address. And if I do that in in decimal format, that's evil. Well, at least that worked. I don't like having or decimal for all of them, but it's better than nothing. So now if I shift it left 3, I get 800,000, call malloc, and I think this is probably due to my renamed registers having not been coordinated and tested with the structure of this stuff. All right, so when we get the address back, it is not 0, which means it's succeeded, and the address is a big number. What does that mean? It's just part of the heap. So if we want to save the value of something that we've allocated, then we need to move that value into X, I believe is which one I have done that with. Now, if I have the array X and I want to initialize it with some values, I think I will now write a function to allocate. Come on. Can't make that smaller? All right, I made it a little smaller. So we have the code for, I'll call it create. And the code will be the same thing. Push RBP and then move into RBP, RSP, and then reserve so that I can tell it I don't need any local variables, but here it becomes a little more important. I'm going to call malloc in here, and to call malloc, right, I need to have space on the stack. In case I run the same program under Windows, I have to have space on the stack for the 4 register parameters to be copied onto the stack. So if I call reserve 0, I'll get the space on Windows, and nothing happens with reserve 0 under Linux. All right. And when you call malloc, it has the value you want in the accumulator register, or RAX, as we already did it. So if we move that value in here, now we can call create, and we can allocate multiple arrays. and they can all be the same size. So the second array can be Y, and the third array can be, I believe that's the three names that I've used. Yes. We will soon hit some more fun. All right, let's see if this works. Ooh, SIG illegal instruction. What could have gone wrong? Run it again. Instead of stepping past the function create, let's tell it to run the program. And we'll use the step into instruction, push RBP. Does anybody believe that I made an error in this code, or is it just simply something goofy?
Probably something planned.
You believe, but I don't. Let's see if we can get any clues from looking at these registers. RDI, let's run it this way. Well, and we have a valid looking stack pointer, and we've got a shift left as the next instruction, and it looks like it did that successfully. RDI is C3500, which is probably going to work fine if I convert it to decimal. Oops, I didn't expect that. All right, 800,000. And I'm assuming that when I call malloc, it's going to get an illegal instruction again. I don't have an excuse. So what I'm going to do is kill this and start it over again. I don't want to step into the malloc code. Oh, it's dying again. I've named functions create before. And it's entering my create function. I don't think malloc calls a create function. If it did, it should be going into my function. Let's see what happens if we run it again and go ahead and step into the code for malloc, see how far we get. Hasn't died yet. Wow. I think it's still in the program. Let's see what it said here. Could not interpret an address. That's an address and something in there. Let's tell it to continue and see if it dies. Yeah, it did. It's further down into malloc code. All right. Does anybody have any clues?
It would be nice if we could see it.
Oh, yeah.
Hey guys, I gotta drop off. I'll talk to you later.
All right. We'll see you later. All right. The best guess, we've seen code with par 1 in use before, and maybe create is somehow in use, but I'm pretty sure that I've called functions create before. So let's change it to create x and see if we can figure it out. No difference.
Yeah, I have just gotten to join you. Am I the only one left, Dr. Ray?
Possibly. There may be people who are viewing it on YouTube, and I'm not sure if they would show up or not.
I see. YouTube people wave.
All right, so the code is move that number into RDI, call create x, move REX to that, and then create x, push RBP, move RSP to RBP. That looks like a normal beginning to a function. I don't have a leave. It's when I come back from malloc. This x had nothing to do with it. My memory was correct on that, but my accuracy on doing things is not 100%. It's kind of odd. You don't get much of a clue from knowing that you had an illegal instruction.
Right.
If you don't do the leave, then the return address is going to be an address on the stack. It's easier to explain it than it was to guess it. All right? The return address was on the stack when we entered this create function. Then we push RBP. So the return address is going to be the previous address of the value that RBP had in it, which was, Jesus, I don't even remember. Whatever RBP was, which wasn't a return address, it was something goofy on the stack probably, and it proceeded to go doing some instructions at work until it runs into one, whatever the garbage was, it eventually doesn't work out. So now I think there's a pretty good chance that I'll create 3 arrays. All right. And we got 3 arrays, no doubt 3 different addresses. Now let's do a function to fill array X with some numbers. So we'll move into parameter 1 the value of X. And as you might realize, X is one quad word and it holds an address. So I'm going to call the fill function. Let's see, I want to tell it, how about if we fill the array with the value PAR 2D, fill it with 7, and then we'll tell it how many to fill it with, and that will be, and it's not supposed to be RAR 3.
I was going to ask you, is it PAR or RAR?
Yeah, it's PAR. We might get lucky and there not be another PAR. Parameter 3 was the value num. And we discovered earlier that n is probably my fault. Most things tend to be my fault when programming doesn't work. But I think that that's the case. I'm going to fill X with 7s and Y with 8s. So to call the fill function, all right. These are longs, and it doesn't really matter what we call them. This is a comment anyway, and the value was the second parameter, and then the number. And before I do anything else, I think I'll put in a leave. That was painful figuring that out. Don't want to figure it out in one day. The second time wouldn't be too bad, probably. All right. So now we've got X in PAR1 and want to fill values in there. And we could use STOSQ, store string Q, but I'm going to just use regular loops. So I'll do a for loop for I equals 0, I less than the number, I plus plus, which I forgot earlier when I did a loop. I want to put a semicolon on this line. X bracket I equals the value. All right, so we'll start with zeroing out a value for our register for I, which will be scratch 1. And then we've got a label for the top of the loop, which I'll keep it FORTOP for top. And then after we get back to this, we want to verify that I is less than num. I is going to be in scratch 1D, so we do a compare. Scratch, well, but just scratch 1 with, well, what is number? That's the third parameter, right? And then jump not less than to about dot end for. Oops. Label by itself must have a colon. So if we get in here, then we need to do the statement in the loop. Well, that's going to be something. Move into the register, which is PAR1 is the register for that, and scratch 1, and I prefer to put the 8 on the other side. How about 8 times scratch 1? Scratch 1 is I. So we get that, and we move the value, which was PAR2. So simple. And this time I'm going to remember, I don't want the D to increment scratch 1. I feel so good. I'm not having to think about which register is parameter 1, which register is parameter 2, which is parameter 3, which ones can I use without having to worry about saving them for posterity's sake. All right.
Now, Dr. Ray,
Yes.
right about line 30, actually line 26, there's par 2D.
Yeah.
Is that intentional?
It doesn't really matter. If you use par 2D, you're selling it to use the double word part of the register. So we get a 7 in par 2.
I see. Okay.
So if you try to fill a 32-bit register, it fills out the upper 32 bits of the 64-bit register. And now I want to step into the fill function and observe it slightly. Scratch 1 is 0. We move the first one in there. Increment, it equals 1. Oh, I made another boo-boo. I remembered the increment, but I didn't remember to jump to back to the top of the loop. And one advantage of using local labels, .4, .n4, and such, is they're restricted to be within the confines of the most recent global label, which would be fill. So if I wrote another function, I could use .4 top and .n4 again. Now let's see if we get into the fill function. If we do this loop more than once, yes, back to 4 top. Now I believe that the program is smart enough to let you do a little bit of breakpoint modification while you're running it. Let's see if that's true. Catch it on leave. Yes, it caught it on leave, and scratch 1 is some nice number, decimal format, all works. It's 100,000, so it ended when that equals it exactly. All right, one more cheap thrill that I can do here.
Come on and have a seat.
I've invented, for more complicated code, a macro named alias, and I'm suggesting that you use uppercase letters for the first letter of these, and we're going to make that power 1.
Okay, Dr. Ray, I've got to bow out again.
All right, I'm going to finish this, and then I'm going to shut up. So you can leave if you wish, but I'm going to finish this off for whoever's watching it at some other time.
Absolutely.
So I've got
guys.
an I alias, and what I can do here is, oops, instead of using scratch 1D, I'm going to use a D and then an I. And here, instead of comparing scratch 1, I'm going to use Q and then an I. So that is the same thing. When I did the assign or alias for I got QI, DI, WI, and BI. And instead of par3, I'm going to use qnum. And instead of putting par1 in here, I'm going to use qx. And here it is qi. And this one is qval. And we're going to increment qi. So by using alias, it is absolutely no value for a very short function. And it is really handy when your function gets a little complicated. I've rewritten the binary tree code using this, and I got to use things like T for tree, P for pointer. Not very handy, but it's better than whatever I might use, register, RDI, RSI, and all that stuff. So I had several things like that that I wrote, and I've rewritten the correlation code using the AVX registers, and there I used an equivalent kind of thing for floating point aliases, FP alias, and I had, instead of doing things with XMM0, XMM0 became, or excuse me, YMM0 for that, became Y sum underscore X. So I named the floating point registers with something meaningful to the application at hand. And I found that that made that program make a lot more sense. I felt more likely that I might get something like that correct quicker using this than just using the original register names. Don't think we have any question and answers. Features disabled. Chat, people are gone. There's one viewer somewhere. Bye. I've done enough. See you next time.